Alright, so we stated that we could determine electron configuration by using Aufbau principle, where we would fill the lower energy orbitals, subshells, energy shells, right? Now, I asked you guys to memorize a certain method and just kind of memorizing which orbital and subshell and shell comes first. You can actually use the periodic table to look at this order following Aufbau principle. So I'm just gonna write Aufbau principle here. But the periodic table is actually a really useful tool that we can use. We can look at electron configuration, specifically the filling of Aufbau principle by Aufbau principle. And what I want to do here is I want to look at the periodic table. I'm going to divide the periodic table to indicate specific orbitals, subshells, and energy shells. Okay. First thing you want to look at here is the periods, which are the horizontal row. Right. The periods are basically the valence shell number. Okay, so the periods are the valence shell number. So what that means is that hydrogen's valence shell is the first shell, lithium's valence shell is the second shell, nitrogen's valence shell is the second shell. This tells us that the valence electrons will be found in the second shell, right, for nitrogen. Right, so the valence shell number is just the horizontal row, so you can see that I've numbered them 1, 2, 3, 4, 5, 6, 7, right? Also, you can see that there is a series, there's a table here, right? So we can notice that if we look at group 6, we have cesium, barium, lanthanum, and then we have the lanthanide elements, right? Because it goes 57, then goes 58 to 71, right? These are the lanthanide elements. Okay, here, and so this is going to still be, it's still going to have a valence shell of 6. Right, and here, if we look at period 7, we have francium, radon, acetium, right, and these are the acinide elements, right? So it continues from acetium and then thorium, etc., right, all the way to atomic number 103, right, and then it continues here. So this is also going to have a valence shell of 7. So the period will tell us the valence shell. Right, so that's really important to understand, because when we're looking at chemical reactions, we're looking at the valence shell in particular. Now, we know that the groups, which are these vertical columns, right, the periods are the horizontal rows. The groups are actually associated with particular orbitals, right? So associated with particular orbitals. So I'm going to show you guys that. And this is how we can actually organize the periodic table in terms of orbitals, subshells, electron shells. Now I'm going to take this helium here. I'm going to move this helium all the way out here. So pretend that there is a helium. I move the helium here. Okay, so this is our helium element, right? And the reason I've grouped this together is because this region here, all of this region here represents the S subshell. Okay, so all of this is the S subshell. Okay, and the S subshell, we know that it contains one S orbital, and orbitals can hold a maximum of 2 electrons. So we can consider this S1 and S2. Okay, so all of everything in this group here has a valence shell that ends with S1. All of this in group 2 here has a valence shell that ends with S2. The ones that end with S2 are what we call spin paired. The ones that end with S1 are half filled, right? So like hydrogen 1 here is basically going to just look like this. It's just 1s1, right? So it's just going to be a half filled orbital. But if you look at beryllium, I'm just looking at the valence shell, right? So in the second energy shell, right? So in the second energy level, you're basically going to have a spin pair 2s2 subshell, okay? And we can explain, we can use the condensed electron structure, and we can write this as helium on the outside, and then we can write the valence orbital out there. Right? So this is a really useful tool in telling us what the valence orbital looks like, right? and each of these numbers corresponds to a particular valence shell, and we can utilize the condensed electron configuration. Like for instance, if I use magnesium, which is magnesium 12, well, this is basically going to look like neon for condensed electron structure, and then we're just looking at the valence shell, so we have 3s1, 3s2, so it's 3s2, right? So we just write 3s2, and what that looks like is just a spin paired s2 orbital. So this is like the condensed electron configuration, right? So it's really useful to kind of understand that. So this is what the first column looks like, right? So that's the S subshell. Okay, so we looked at the S subshell region here. We'll call this specifically the S block, right? The next block that we're going to be looking at is this region here. And this guy here is called the P block. Okay, so I'm just going to highlight that region. Okay, so this is called the P block. Okay, and we know that the P block represents the P subshell. Right, and the P subshell starts in the second energy level, right? So this is the 2p subshell, this is the 3p subshell, 4p subshell, 5p subshell, 6p subshell, 7p subshell, right? Or in other words, this is basically the 2p subshell, this is the p subshell in the second energy level, right? So we can actually kind of correlate the energy levels with each particular subshell. Okay, so you can think about this as your value of n. Right, well, let's use a different color here. So you can think about all of this as a value of n. N is basically your shell number, right? So just make a note that n is your shell number. Okay, so all of this, you can think about each of the rows, the periods, as your shell number. Now, this is your P block in orange, right? And we know that the P block can hold, the P subshell can hold 6 electrons. It's because the P subshell is composed of 3p orbitals. Okay, so this is basically P1, P2, right? Well, specifically, you want to write this as a subscript, a superscript. Sorry. So this is P1, P2, P3, P4, P5, and then this is P6. Okay, and you can understand that there's going to be three. Oh, sorry about that.
Hi, you're a giant. I'm your assistant.
Right, so we know that the P subshell contains 3p orbitals, right? And basically, a p orbital would exist in this region. You know what? I'll just use a slighter shade. Okay, so there's going to be a p orbital here. So these two are going to be one p orbital. These two are going to be another p orbital, and then this is going to be your final p orbital. Okay, I think it'd probably be easier if I redraw that. Okay, so this is one of the p orbitals. Right, this is the other p orbital, and then this is the third p orbital. Right. So I think earlier I showed you guys what a p subshell looks like. Right, it consists of a px, a py, and a pz orbital. You can think about this as px. You can think about this as py. And you can think about this as pz. Right, so those represent the 3p orbitals. So it's really useful to understand that each block, each set of two, right, each set of two here would represent an orbital, right? And just like what we saw here, right, the set of two here represents one s orbital, right? And each of the s orbitals will be found in different periods, right? So that's the idea behind it, right? So this is really useful to understand. So for instance, if I was looking at, I'm just gonna make some space here. Right, so if I was looking at, let's say we're looking at carbon, right? And if I was just looking at its valence shell, well, in this case you can write this as helium, right? And then the valence shell is going to be in the second shell, the second period. So we're going to have 2s2, because we're in the second energy level. So 2s1, 2s2. Then 2p1, 2p2. So we always go left to right, and we can do the condensed structure. So if we were going to draw electron configuration of this, right, then basically this is your S subshell, will look like that, and then your P subshell 2p2, we have to use Hund's rule, so it would look like that. Now obviously you would need to show an incremental energy difference, but for the time being I'm just going to explain it like that. So this is what your electron configuration looks like, right? So it's really useful to kind of understand how this works. Like if I was going to look at sulfur, which is 16, right? So this was carbon 6. If I'm looking at sulfur 16, right? If you're looking at the condensed structure, you look at neon, and then you go. When we're looking at sulfur, it's in the third energy level. The valence shell is the third shell. You have sodium 3s1, magnesium 3s2, aluminum 3s2 3p1, silicon 3s2 3p2, phosphorus 3s2 3p3, sulfur 3s2 3p4. So it looks like that. And then all of this is your valence shell. Right, so this is a shell that's going to be useful in reacting, right? So, and then basically if you wanted to draw this out, if you're looking at sulfur, then you'd have neon, and then 3s2, so this would be spin paired, and then basically, I'm just going to erase this, make some space here, right? And then you would have, first you would basically half fill, and then you would spin pair, because we had 4 electrons, right? So this is why it's really useful. So that's the P block. So the next block we're going to be looking at is the D block. Now the D block extends from here all the way down to here. Okay, so all of this is the D block, right? And you can notice here that the D block represents the D subshell, right? And the D subshell should have 5 D orbitals. So if you have 5 D orbitals, well, this is one D orbital. This is another D orbital. Third D orbital. Fourth. And that's your fifth. So if you wanted to kind of label this, I'm just going to clear this up a little bit. If we wanted to label this, well, we can call this D1, right? So this is one of the D orbitals, right? D1, D2, whoops, sorry guys. D1, D2, D3, D4, and D5. So these are the 5 D orbitals, right? But we want to specifically look at each orbital specifically, right? So I'm going to call this, right, so this is D1, whoops, right, so this is the electron in one of the D orbitals. D2, this is D3, D4, D5, D6, D7, D8, D9, and D10. So that's consistent with our D subshell, right? So for instance, if I wanted to look at the electron configuration of manganese, which is 25 atomic number, right? So if I'm looking at manganese, right, so what you want to do, let's do the condensed method. So we would write argon out here, right? Then from argon we go 4s1, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, right? So it's 4s2, 3d5. Now sometimes in textbooks what we'll see is they're going to put this in increasing order, so 3d5 and then 4s2. Okay, so all of this is a valence shell, and the reason that the D subshell occurs after the 4s subshell is because the D subshell actually expands further outwards, right? So that's something that you want to memorize, but you can actually notice that if you go left to right on the periodic table and you use Aufbau principle, you would go 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and you can actually, you don't have to memorize it, you can just use your periodic table if you know how to read it, right? So that's why this is really useful, right? But it's really useful in determining this. And if you wanted to show this in electron configuration, right, argon, I'm just going to write 4s2 first, order of filling, and then 3d, right? So there's 3d5, so all of these should be half filled. So once again, you have to use Hund's rule, right? Always half filled before spin pairing, right? So that's the idea behind that, right? So that's the D subshell, and let's take a look at the F subshell now. All right, let's take a look at the F subshell. So the F subshell is going to be located here, right, where the lanthanide and aconite elements are. Here are the lanthanide elements up top and the aconite elements. Okay, so here is your F subshell. The F subshell consists of 7 F orbitals. So there's an F orbital here, 1 F orbital here, 2 F orbital here, 3 F orbital here, 4 F orbital here, 5 F orbital here, 6 and 7, right? Now, although this is in the 6th and 7th energy level, the F orbital at the F subshell is always n-2. Okay, so this is the 4F subshell, and then this is the 5F subshell, right? So it's always n-2. Remember that the D subshell is n-1, right? Like this was 3D, this is 4D, even if it's in the 4th energy level and 5th energy level respectively, right? So it's always n-2, so it's always important to understand that. And let's say we were looking at, let's say we're looking at the electron configuration of cerium. Well, if we're looking at the electron configuration of cerium, which is atomic number 58, right, then you would basically, so you're in the 6th energy level, so you still need to use xenon as your noble gas. We're using the condensed structure, so use xenon as your noble gas. Sorry about that. It should be an X, Xe, xenon, and then it goes cesium, barium, so 6s2, right, lanthium, 5d1, and then it goes to the F subshell, and specifically in the 6th energy level, is the 4F subshell, 4F1. Okay? So that's the idea, that's the electron configuration. So make sure you remember that the D subshell is n-1, the F subshell is n-2, right? And you can notice that the D subshell and the F subshell here are half filled, right? So that's really the idea behind it. Right, so if you wanted to look at each of the orbitals, the electrons that occupy each orbital, then this would be F1, F2, F3, F4, F5, F6, F7, F8, F9, 10, all the way to 14. Okay? Alright, let's determine the condensed electron configuration and orbital diagram for the following atoms. So let's start with germanium 32, right? And then we're going to look at iodine 53. So looking at germanium 32, if we're looking at condensed, germanium 32 is located right here, right? So if we're looking at the condensed structure, I'm going to start with the noble gas to its top. It's the top right. So it's argon. So I'm going to use argon as my noble gas. So you do the previous noble gas, and then from argon, because you've included argon, you've considered the electron configuration up to argon. Then you go potassium, calcium, so that's 4s1, 4s2. Then you go to the D block, and remember that the D block is always n-1. So in the 4th energy level, we're going to have the 3rd D subshell, right? The D block is the D subshell. We'll have 3D1, 2, 3, all the way to 10. So this is 3D10. Okay, so 3D10. And then we go to the 4p subshell. So we go 4p1, 4p2. Okay? So you can write like this, right? In some textbooks you would probably order this in terms of their increasing energy level. I prefer to kind of keep it this way, where you can see which subshell has the higher energy versus the other, right? So it's always good to kind of understand that. And then if I was going to do this in orbital diagram, well, this is the 4s2 portion, right? So I'm going to write down argon first. Just write down argon here. Okay, so you write down argon, and then this is the 4s2, and then, so that's 4s2, and then for the D subshell, there should be 5d orbitals, so we have 3d10, so everything should be spin paired, so always half filled before spin pairing according to Hund's rule. But everything here should be spin paired, so this is 3d10, and then you go 4p2, right? So 4p2, you're going to have half fill according to Hund's rule, right? Electrons prefer to be half filled in spin pair. So this is basically what the valence shell will look like. Now let's take a look at, and the valence shell is only particular to the 4 energy level, but we're going to include the D subshell just to demonstrate that it is higher in energy than the 4s. Let's take a look at iodine. So if we're looking at iodine, let's take a look at it here. So this is iodine. Right, and we use a different color. Okay, so this is iodine here, right? And if we're looking at iodine, we can use its previous noble gas, krypton, right? And then from krypton, we go 5s1, 5s2. Erythium, so then we go 4d10, right? Because once again, the D subshell is going to be n-1 of the energy level. So in the 5th energy level, you'll have the 4th D subshell. And then you'll go 5p, 1, 2, 3, 4, 5, right? So it's 5p, 5. Right, so the electron configuration of this, right, you'd write krypton, 5s2, spin paired, then 4d10, right, so you go spin pair all of this. Okay, so 4d10 and then 5p, 5. Okay, it's a half fill and then spin pair. So this is 5p5, right? And the valence shell here, it's the highest energy level. So the valence shell will include the 5s2 and the 5p5, right? I'm just going to write the 4d just to show you guys how these subshells are organized in different energy levels, right? So that's the idea in using the periodic table to determine electron configuration. Alright, let's determine the condensed electron configuration and orbital diagram of first atomic number 64, it's gadolinium, GD, and part B we have atomic number 73, which is TA, which is called tantalum. Okay, so starting with gadolinium, I'm going to take a look at where it is located. So it looks like it's located right here. Okay, so it's in the lanthanide element block, right? So what you want to do here is, well, we have to look at, so this is going to be in the 6th energy level 7, right? So this is the 6th valence shell, 7th valence shell. So if we're looking at the 6th valence shell, then we need to kind of look at the previous noble gas. So the previous noble gas would be xenon, right? So we look at the 5th energy level as noble gas. So I'm going to write down xenon here. And I'm going to write down the electron configuration first. Well, we can understand that from xenon it goes from the 6th energy level, cesium 6s1, barium 6s2, lanthanum 5d1. Okay, so it goes 6s2, 5d1. Then from lanthanum we go cesium, proctium, and so forth, right? So all the way to gadolinium on 64. So, and this is the F block, so F1, F2, F3, F4, F5, F6, F7, right? Now the thing about the F block is that it's going to be n-2. Okay, so it's something to mention. Did I make a mistake? So in the 6th energy level, the F block is going to correlate with 4F, right? So this would be 4F, and then this would be 5F, right? So in this case, you go 4F1, 4F2, 4F3, 4F4, 4F5, 4F6, 4F7, right? So you write down 4F7 for gadolinium. Okay, so this is what your configuration looks like of your valence shell, and the way I'd write this out, or draw this out anyways, is going to be, so this is the 6s2, this is going to be spin paired, right? I'm going to put down xenon out here. Then you have 5 D subshell. The D subshell is going to basically have 5d orbitals. Okay, and it's only one of them will be filled. It's going to be half filled. And in the 4F subshell, it's going to have 7 F orbitals. Right, so this is 4F7. So first draw out each of the orbitals, and then all of them will be half filled. So this is really important to understand. So these all are half filled, right? And yeah, that's your configuration and your orbital diagram. Let's take a look at tantalum, right? 73. So 73 tantalum. Let's use this color. It's located here. Okay. It's located here. We look at the previous noble gas, so it's going to once again be xenon, I'm going to write down Xenon here, right? So from Xenon you go 6s2 cesium barium, and then 5d1, right? Then from 5d1 you complete 4f14, right? You go cesium all the way to lithium, atomic number 71, and then so 4f14, and then you go back to atomic number 72, right? So this is 5d2 and this is d3, right? So you can see that it goes 5d2, d3, right? So you want to include this back to there, right? So you only have to write down the 5 one time. So this is going to be 5d3. Okay, so you can see that this is the highest energy subshell and orbital, right? So the 5D subshell actually spans a little bit further than the 4F subshell, so this is really important, right? So in terms of order of subshell energies, you can write this as 6s2, 4f14, 5d3, and if I was going to draw the orbital diagram, you write down Xenon, and you go 6s2, spin pair, 4f14, which is going to have seven orbitals in that subshell, right? And this is going to be completely spin paired. Okay, so this is 4f14, and then 5d3 right? So this is going to be half filled, right? So this is 5d3. And yeah, that's the idea of electron. Alright, determine the condensed electron configuration and orbital diagram. And this time we're going to be looking at ions. So magnesium plus 2, well in this case, the plus 2 here indicates that magnesium has lost 2 electrons, right? And the 2 electrons that it'll lose are from the valence shell. So I'm just going to write down the electron configuration magnesium 12, right? So it's going to look like 1s2. Well, actually, let's look at the condensed electron configuration. So if you're looking at just normal magnesium, the condensed electron configuration is neon 3s1, 3s2, right? So this is 3s2. The 3s2 is the valence shell. Now, in magnesium plus 2, we've lost those 2 electrons, right? So in that case, if you lose those 2 electrons, then it's going to basically just look like neon, right? So that's what the second question is, and that's one of those things that I want you to kind of see here. That neon is basically, I'm just going to write the full electron configuration of neon, or you can use helium, right? You can use helium and then 2s2, 2p6, right? But basically magnesium plus 2 and neon are going to look exactly the same. So when 2 different species, and the reason we call them different species is because they have different number of protons. If 2 different species have the same electron configuration, we call these isoelectronic, right? So magnesium plus 2 and neon are isoelectronic. They have the same electron configuration. Okay, now let's take a look at part C here. We have iron plus 3. Iron is 26, so iron is going to be located here, right? And let's look at the condensed electron configuration, right? So we do argon, and then we go 4s1, 4s2, and then 3d1, 3d2, 3d3, 3d4, 3d5, 3d6. Okay, 3d6. And if we're looking at drawing out the orbital diagram for this, so this is 4s2, and the D subshell has 5 d orbitals. So I'm going to half fill first, and then spin pair secondly. So this is 3d6. Okay, so that's the idea behind it. Now this is original. This is iron by itself. Now if you're looking at iron plus 3, right? So this I just drew. This is normal iron. If you're looking at iron plus 3, then you're going to have to remove electrons from the valence shell. Now, the idea with this is that you always remove electrons from the highest energy level, so you always remove electrons from the 4 first, and then the 3D subshell, even if the 3D subshell is a little bit higher in energy, right? So the way you'd write this is you'd write this as Argon so you deplete the electrons in the 4s2, and then you subtract 1 from the 3D, so it's just 3d5. Okay, so now what it's going to look like is Argon (3d5), and all the electrons are half filled. So when you're taking away electrons, you always take it from the highest energy level, even if one of the subshells with the lower energy level is higher than the higher energy level, right? So it's always take it from the higher energy level first and then go to the lower energy level. So that's the idea behind it. Okay, let's take a look at the condensed electron configuration of tin and lead. Okay, so tin here is atomic number 50, and lead here is atomic number 82. Okay, so start with tin. So if we're looking at +2, then we've lost 2 electrons. I'm going to look at original tin first. Okay, so 50. I'm just going to write down it's a condensed electron configuration. So if you're looking at tin, you look at its previous noble gas, a krypton, and then you write down 5s2, because it goes rubidium, strontium, 5s2, 3d10. Right? Oh, sorry about that. 5s2, 4d10, because D subshell is n-1. So 5s2, 4d10, right? And then it goes 5p, 1p2, right? So 5p2. Okay, so the valence shell here is all of this. Specifically, it's the 5th energy level, right? If you're looking at +2, right? So 10 plus 2, you're gonna have to remove 2 electrons from the valence shell, which is the 5p2. So you're actually gonna get krypton 5s2, 4d10, and the 5p is missing, right? So, and technically we would put this in order, but we're just kind of showing it to you this way because it's easy to keep track of the energies. So here is krypton, right? 5s2 is spin paired, and then we go 4d10. Right, so there's going to be 5 d orbitals in the 4d subshell, and you're going to get something like this. Okay, so that is the electron configuration of 10 plus 2 cation, right? And it's a cation because we basically have 50 protons and 48 electrons, because you've lost 2 electrons. So +2 means you've lost 2, -2 means you've gained 2, right? Okay, let's take a look at lead, lead 82. So the atomic number is 82 here, so we're basically looking at this guy. Okay, so if we look at just lead by itself, I'm going to use Xenon as its previous noble gas, then it goes 6s2, right, 5d1. So this is pending because then we go the lanthanide elements. So 5d1, 4f14. So remember that the 4th energy level is n-2. This is for the F subshell or the F block, and n-1 for the D block. Okay, so we have 4f14. This goes all the way to atomic number 71. Then we go 5d10 all the way to mercury, right? So I'm going to write down 5d10. Let's do this in order in terms of energy. So 4f14, 5d10, and then 6p1, 6p2. Okay, so the valence shell here, specifically in terms of the energy, is going to be the 6s2, 6p2, right? In this case, the energy level was basically 5s2 and 5p2, right? I just wrote down these guys just to show the continuum of energies associated with the subshells. Now, yeah. So this is your elemental electron configuration, but now we have a +4 here, so we've lost 4 electrons. So you need to lose electrons from the highest energy levels, right? So the 6p2 and then 6s2. So in that case, what you're going to get here is pb +4 if you remove electrons from here and here, that cancels out, and you actually get Xenon 4f14 5d10. Okay, so this is what your new electron configuration looks like. And then if you're going to draw this out, so you write down Xenon, right, 4f14, well, you have to draw out 7 f orbitals here. This should be spin paired. Okay, so it'll be spin paired here, so this is 4f14, and you also need 5d10. So this also should be spin paired as well. Okay, so this is your orbital diagram, 5d10. That's the idea behind it. Alright, let's take a look at the electron configuration of copper. And the reason I'm looking at copper is because this actually demonstrates a prominent exception, right? So we would expect the electron configuration of copper here. I'm just going to use the condensed method. So if we're looking at copper, then we're going to be using this previous noble gas argon. Then we go 4s2, 3d, 1, 2, 3, 4, all the way to 9, right? So this is 3d9. So you'd expect the electron configuration to look like this, but in actuality, so this is your expected case, but in actuality, copper 29 looks like this, argon 4s1, 3d10, right? And really the difference here is that one of the electrons from the 4s orbital jumps to the D subshell, right? So one electron jumps from the S subshell to the D subshell. So this is what we actually call an exception, right? And this is something, this phenomenon is called an electron transition. Okay, so let's take a look at the orbital diagram now. But in this case, now your 4s orbital is half filled and your 3d orbital tends to be fully filled, right? It's spin paired. Every orbital in the D subshell is spin paired. Okay, and the reason this electron transition occurs is because of the fact that it is more stable. So it is more stable for the D subshell to be filled than having the S subshell filled. So the more likely that the D subshell is filled, right, the more stable that the species is. So that's why there is an electron transition, that an electron actually will jump from the S orbital, right, the S subshell to the D subshell, right? So that's why you get this S1. Another exception of this, and the two main exceptions, are copper as well as chromium, right? So you can also look at the electron configuration of chromium, and the electron configuration of chromium, normally you would expect argon 4s2 3d4, but you're actually going to actually see 4s1 3d5. So anything that has an electron transition, the s orbital isn't completely filled because there's an electron transition from that s orbital or subshell to the D subshell, because it's more stable for the D subshell to be filled. Okay, using the quantum mechanical model, construct the atomic structure of elemental phosphorus. So once again, elemental phosphorus means that we have 15 protons but 15 electrons as well. Same number of electrons as protons. We have 16 neutrons, right? I'm going to account for these 15 electrons. Now when we're looking at the electron location using the quantum mechanical model, electrons are located in orbitals. Orbitals come together to form subshells, and subshells come together or coalesce together to form electron shells. Okay, so I'm going to look at all of these cases, and two important rules that we need to kind of take advantage of when we're constructing these atomic structures using the quantum mechanical model is Aufbau principle, which states that you always fill lower energy subshells, energy shells and orbitals, and then higher energy versions, right? So we need to also look at Aufbau principle. We need to also look at Hund's rule, And Hund's rule states that you always half-fill orbitals before spin pairing, because electrons prefer to be half-filled to minimize repulsion forces, right? So we looked at Aufbau principle using a really good way to memorize it, right? So you write down all the subshells out here, right? The way I'm doing it right now, right? 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? And in this case, what you want to do here is you just go this way to fill. And this is the direction of filling, right? You follow the arrow. You always fill 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, right? And there's an exception between the 3d and the 4s. The 3d actually, the 4s is filled before the 3d because the D subshell spans past the 4th energy level. So the 3D subshell is actually higher in energy than the 4s subshell, right? Relatively, they're about the same energy, right? But the 3D is a small increment higher, right? So I'm going to construct this, right? Similar to our previous example. If I'm constructing this, I'm going to put energy on my y-axis, my vertical axis, and I'm going to put this as my base. Okay. Using the grid system, I'm going to move up 2 spaces per each subsequent shell and so forth. Right now, for each of the subshells, I'm going to use red for s orbitals, and thereby the s subshell. I'm going to use orange for p orbitals, and I'm going to use yellow for d orbitals. Okay, so let's start off with our first shell. Okay, so I'm going to start off here, and in our first shell here, okay, so this is n is equal to 1. Right, in our first shell we should have an s subshell. Right, in the first energy level we only have an s subshell. Right, an s subshell is only composed of 1 s orbital. Okay, so this is the 1s, right? And basically we would have a filling of 2 electrons. So the first electron is filled this way. The second electron is filled in opposite spin. So this is why we say that spin paired. If the up arrow means that it's clockwise, then the down arrow means it's counterclockwise. But it doesn't necessarily have to mean clockwise. If the up arrow means counterclockwise, down arrow means clockwise. So it doesn't really matter. It just means that they just have 2 opposing spins, right? And in this case, they have 2 opposing spins, and then the idea here is after we fill the 1s subshell, we then fill the subsequent subshell. So I'm going to move 2 spaces for the subsequent subshell. So this is the 2s subshell, right? So this is, well, in this case, this is the subsequent energy level. This is the second energy level. In the second energy level, we actually have 2 different types of subshells. So one of the subshells here is the 2s. So this is the 2s subshell, right? But we'll also have the 2p subshell. Okay, now the 2p subshell is going to be made up of p orbitals. Okay, so this is the 2p subshell, right? It's made up of p orbitals, and what we're going to do here is we are going to fill the 2s subshell first. So we always half fill orbitals first, then we spin pair it. According to Aufbau principle, we need to finish filling the 2s subshell, then we move to the 2p, right? And the 2p is going to be higher in energy, and the vertical axis here is energy. Okay, so we have energy on the vertical axis. You can see that this is higher. The p subshell is higher than the s subshell here. So we always half fill first. So using Hund's rule, half fill first, then spin pair it. Okay. Now we can also denote each of the orbitals containing electrons using a superscript. So what I mean by this is in the 1s subshell we have 2 electrons, so we can put a 2 up here. In the 2s subshell we have 2 electrons, so we put a 2 here. In the 2p subshell we have 6 electrons, so we put a 6 here. Right? So technically we can represent each subshell using, I'm just going to write here, n for the energy level, x for the type of subshell, and a as the number of electrons that occupies the subshell. So number of electrons in each subshell, right? This is the subshell type, and this is the energy level of the subshell. Okay, so we can represent subshells in this format. You can see this using different variables. I just used n, x, and a. Okay, so we've accounted for 10 electrons now, right? So this is the second energy level, this is the first energy level. Now what we're going to look at here, that's 10 electrons, we need to account for 5 more electrons. Now we need to go to the third energy level. So if I'm looking at the third energy level, we jump to the third shell, right? Okay, so this is, right, this is the third shell. So this is the 3s subshell, right? And in the third subshell, we're going to fill 2 electrons, right? We will spin pair that. And the third energy level, I'm going to indent one more space for its subshell. So in the third energy level, we'll have an S subshell, a P subshell, and also possibly a D subshell. Now we don't need the D subshell here because we'll actually account for all the electrons. So this is the 3p subshell. Okay, you can see that the 3p subshell is higher in energy than the 2p subshell, right? And because we've accounted for 12 electrons, I need to fill 3 more, right? And we use Hund's rule again, so we're going to still use Hund's rule where we always half fill before spin pairing, right? So if we wanted to write this using the numbers of each electron in each subshell, there's 2 electrons in the S subshell, in the 3s subshell, and there is 3 electrons in the 3p subshell. Now we're just looking at the subshells, but you can also look at each of the orbitals that make up the subshell as well. Like this is 3px, right? This is 3py, and this is 3pz, right? This was 2px, 2py, 2pz, right? And you can also denote the number of electrons in each orbital within the subshell if you want, but our focus is the entire subshell, right? So this is basically the layout of all the electrons. Now collectively I can write this as all the electrons in this atom can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3p3, right? So technically this is the configuration or the arrangement of all the electrons in this atom, right? And this is what we call electron configuration. So I'll take a look at some electron configuration examples next, but I also want you to understand that within this atomic structure, these are the adjacent, these are each of the individual shells, so I'm just going to highlight that. So this is the first energy level, right? So this is the first energy shell. This is the second energy shell, right? So it includes the S and the P. And then this is the third energy shell here, right? So this is n is equal to 3. The third energy shell should also have a D subshell here, but no electron is occupying that, so we don't care about it, right? So this would be the 3D, but there is no electrons occupying that. And you can notice here that this subshell, this energy level located here, I'm just going to highlight that. This energy level that's located here, this is the furthest energy level or energy shell from the nucleus, and this is what we call the valence shell. So this is the valence shell. It's the furthest electron shell from the nucleus. As a result, these electrons have the most amount of energy because their separation distance is the highest. So this is going to be really important because we know that the valence shell contains the valence electrons. The valence electrons are the most energetic electrons found in the atom, and as a result, they're the ones that are really involved in creating chemical reactions, right? They're involved in chemical reactions. Okay, determine the electron configuration of the following ion and construct its atomic structure with association to the quantum mechanical model. And the ion we're looking at is calcium plus 2, right? Now, when we're looking at writing the electron configuration, we need to pay real close attention to Aufbau principle, which states that we always fill lower energy shells, subshells, orbitals first, and then higher energy. So, a calcium ion means that we basically have lost 2 electrons. So normally calcium by itself has 20 protons and 20 electrons. We don't really care about neutrons, but it has 20 neutrons. The neutrons and protons won't change. Protons and neutrons only change in nuclear reactions. In chemical reactions, we only have changes in electrons. Now, this is calcium, but calcium plus 2 means that we've lost 2 electrons. So as a result, we have 20 protons, 18 electrons, and 20 neutrons. So this is why you have positive 20, negative 18, and then as a result, you have plus 2. So if I look at the electron configuration of normal calcium or elemental calcium, right? In this case, you should have 1s2, 2s2, 2p6, right? So these are these subshells and orbitals are filled, right? So that's a total of 10 electrons. Then we go 3s2, 3p6, 3p6, so that's 18 electrons. Then 4s2, so that's 20 electrons in total, right? And the way I'm filling it, you use Aufbau principle, and you can memorize this using this notion. Let's just get rid of the numbers on top. 2s, 3s, 3p, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? So you would basically fill them, and you can put the electrons actually that cover each subshell. This is the maximum filling of each subshell. It doesn't really matter, right? 2, 6, 10, 14. You always fill these subshells and orbitals, their respective orbitals and energy levels in this manner, right? So you guys can just memorize this for the time being, right? And so forth. Now, in the calcium ion, you're going to have 18 electrons. So you have 1s2, 2s2, 2p6, 3s2, 3p6. Now the 4s subshell is missing the 2 electrons. So this, if you look at this, this is its actual valence shell, right? So the valence shell loses electrons. It loses the 2 valence electrons. So these are the 2 valence electrons, and these 2 valence electrons are lost, right? And this is essentially what's happening in a chemical reaction when calcium reacts with, right? If we're looking at like an ionic compound, and calcium, a metal, reacts with a non-metal, right? The 2 electrons are basically removed or transferred. So this is basically calcium, and outside the valence shell, we have the non-reacting shells that are filled shells, and these are called the core electron shells. Okay? So in the calcium ion, we're just left with the core electron shell, and we essentially form a stable octet. That means a filled shell. And you guys can actually group each of the different types of shells in the electron configuration. Like this is the first shell, right? This is the second shell. This is the third shell. And then this is the fourth shell, right? So you can see that the valence shell is removed, and now you actually only have 3 shells left. So this is the first shell, second shell, third shell. Okay? So now I'm going to construct the calcium ion quantum mechanical model. So to do that, I'm just going to put energy on my vertical axis, right? And I'm going to put, okay, so this is energy here. Okay, and let's start off, and I'm going to say that each square shift upward is an adjacent or subsequent subshell, and each 2 shifts of cubes is going to represent a different energy shell, right? So this is going to be n is equal to 1, right? This is n is equal to 2. This is n is equal to 3. Okay, so I'm going to use these as my benchmarks, and I'm going to use colors to represent each subshell. So this is the s orbital, part of the s subshell. This is the p orbital. Whoops, let's use orange for p orbital. Okay, I'm just using circles to represent orbitals, and I'm going to use this is the d orbital. Okay, and we can use a different color for f orbitals, but we won't even have a d orbital here. Now in the first energy level, we're only going to have one s subshell, so this is the s subshell here. Okay, this is the one s subshell, and we're basically going to be, this is going to be filled, so this is the 1s subshell, and we're going to be spin paired, right? So one electron spinning either clockwise or counterclockwise, and the other electron in its opposite spin. Right, so this is 1s subshell, then we indent 2 spaces, we go to the second energy level, and we're going to have also an s orbital there, so there's an s subshell in the 2. Second energy level, this is a 2s subshell, right? We fill this with electrons, so we have electron there, spin pair, using off-ball principle, we go to the next subshell. So the next subshell, we're going to indent 1 space, so it's important to understand these indents, right? We indent 1 space, and then we have p orbitals, so there's going to be 3 p orbitals in the 2p subshell. This is 2px, 2py, 2pz, right? And in this case, I'm going to half fill orbitals first, and then I spin pair. So this is a total of 10 electrons. I need to, because I'm looking at the calcium ion, I need to accommodate for 8 more electrons. I go to the third energy level, and I'm going to create the 3s subshell. So this is the 3s, right? I'm going to fill these guys up. Okay, so this is 3s, right? And then I look at this is my 3p subshell, and there's the 3p orbitals. Okay, and call this 3p X, 3py, 3pz, right? But we only need this subshell. We don't need to consider the D subshell. So now we need to accommodate for all of these electrons, right? So spin, half fill first and then spin pair, and that's all 18 electrons. So you guys can see here that this is, all of this is the third energy level. All of this is the second energy level, so this is n is equal to 3, this is n is equal to 2, and all of this is the first energy level. And you can see that the third energy level, the valence shell, which is this, is completely filled, and we have a stable octet. Right? All elements will react until they form a stable octet, and that's essentially what it looks like. Right? So we represented the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6. Now because this calcium ion actually mimics argon, right? We know that argon is basically 18 protons, 18 electrons, right? Calcium ion actually mimics argon, its electron configuration. So as a result, you can actually represent the calcium ion as argon. So the electron configuration of calcium can just be written as argon, right? So this is the electron configuration, but there is also a condensed electron configuration, where if you wanted to look at just elemental calcium, you can write it as argon and then its valence shell, right? So this is basically 4s2, and this is basically the valence shell, right? So this is the condensed electron configuration. So I'll look at some examples of electron configuration as well as condensed electron configuration. Okay, write the full and condensed electron configuration for the following atoms. We have 24 chromium, or chromium, which 24 protons is elemental chromium, and then rubidium plus 1. Okay, so elemental chromium, we have 24 protons, 24 electrons. I'm not too concerned about the neutrons right now. And as a result, we're going to write this as 1s2, 2s2, 2p6, 3s2, so that's already 12 electrons. Then we have 3p6, right, 4s2, so that is 20 electrons. Then after the 4s subshell, we have the 3D subshell. So we talked about how the 3D subshell actually appears a little late, and it's actually further stretching than the 4s, so that's one of the exceptions. And then we basically will have 4 electrons occupying the 4D subshell. Okay, so this is the full electron configuration. Now the condensed electron configuration, if you use your periodic table, guys, you look at the previous noble gas. So you look at this is the noble gas argon. Okay, all of this is argon, and then we just write the valence shell. Now what we do, even though the 3D subshell is the higher energy level, we always write it in order, right? So we do 3D 4, 4s2, right? And the valence shell is still the 4s. The valence shell is the highest energy level, right? So the valence shell here is n is equal to 4, right? But the 3D subshell is still higher in energy, right? So for the most part, you want to write this in increasing energy levels, but the 3D subshell is a little bit higher in energy than the 4s. So that's one of the reasons why I switched from this to that, right? It's not a big deal in terms of because I tend to write Aufbau principle to represent the relative energy, so it's not really a big deal in terms of organization. They just do this because they want to keep track of the higher energy levels, right? So the highest energy level here is the 4s subshell, right? So this is the condensed, and then this is the full electron configuration. Then I'm going to look at rubidium, right? So I'm going to do the same thing. So rubidium has 37 protons, but because elemental rubidium has 37 electrons, plus 1 means it's lost 1 electron, so it has 36 electrons. Okay, so if it's 36 electrons, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, so that's constituted about 30 electrons, right? And then we get 30 electrons and then 4p6, right? So that's 36, and then we basically have 5s2. Okay, so this is basically the full electron configuration. You can see that all of the orbitals in each of the shells are completely filled, right? And if you actually looked at the layout of this, right, you can actually replace. Oh, sorry guys, this is 4p6, not 5s2, right? So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. All of this adds up to 36 electrons. And you can actually notice that this electron configuration actually mimics that of krypton, right? And krypton is a noble gas. So this is the condensed electron configuration, right? So it just mimics a noble gas, basically. And this is basically a stable octet. It's stable in the sense that all of the shells, the subshells, the orbitals are filled.